Technical security mechanisms for cyber-physical attacks are not very different to technical security mechanisms for any kind of cyber attack. So there will be firewalls, there will be intrusion detection systems, there will be anti-malware, there will be perhaps whitelisting, cryptography, of course. So all of these types of systems that one might be used to seeing in cyberspace, of course, you would see in cyber-physical space too. So you would see for cyber-physical attacks too. Nevertheless, there are differences. So I'll try here to focus on the emphasis, on the different emphasis that exists in cyber-physical space for the different types of security mechanisms, for the different types of technical security mechanisms. So starting with firewalls. So firewalls are obviously one of the most common types of technical security mechanisms used in any kind of network, especially in corporate networks, in local networks, in enterprise networks. So a firewall can be software-based, it can be hardware-based, and what it is it is a filtering system. So it acts as a barrier between different networks, perhaps the internal corporate network and the internet. And what it does is that it polices traffic. So as traffic comes in, which is ingress traffic, or traffic goes out, so I mean network traffic goes out, so that's egress traffic, it filters them out according to predefined sets of criteria. So it might block some traffic, or it will allow some traffic to go through according to some predefined rules, some predefined sets of criteria that are set. So the image here shows how firewalls can be set in order to act as barriers between the different networks, especially between the control network and the corporate network, or the corporate network and the internet. There is also a DMZ, a demilitarized zone, that contributes to this isolation. So you see the corporate network is here, the internet is here, and the two should not be directly connected without firewalls in between. And of course the same for the control network and the corporate network, which is protected through these sets of firewalls and the demilitarized zone, as we call it. So this helps isolate it, it helps protect to some extent, not completely, but to some extent from any kind of malware or any kind of threat going through networks, so going from the one network to another network. There are different types of firewalls. This is standard kind of firewall classification. There are the firewalls that are the simplest, the most lightweight. We call them stateless because they look at individual network packets in isolation, and according to them in isolation, they take decisions based on some rules which are static. There are the stateful ones which keep a history of the packets that are inspected, so they don't look at them in isolation, but they have a history of the packets. And the proxy firewalls, which act as intermediaries, they establish on behalf of internal networks and any external connections that they require, so they act as proxies. And the deep packet inspection firewalls, which are considered the most advanced, at least in this kind of classification, which take the packets apart, they look inside them, analyze the data, and based on what they see inside this network traffic, that's how they decide whether they will allow something or not. So they are they're much more complex. They're also less lightweight, of course, in this way. And by being less lightweight, it means that you would not see a deep packet inspection firewall to protect, for example, let's say a smart light bulb, because it wouldn't have enough processing power, and it would probably not make sense to do that anyway. But you would see it in between an industrial control network and the corporate network, because it makes sense to maximize the protection in this case, even if it comes at the expense of increased processing needs. So some examples, as I mentioned, would be isolating industrial control network from the corporate network. It might be that's theoretically mainly. I don't think it exists in many actual cars, in many actual vehicles. But you could have isolation of the in-vehicle networks based on firewalls, and there is an element of this in the gateways, but not much. And an important point though with firewalls is that as it has been proven multiple times actually, that firewalls are only as good as their configuration. So it is the human users that can easily make, or human network administrators, I would say, that configure them, that might make the mistakes. And the more complex the rule sets that are defined, the more the errors. This is natural. And as a result, if there are errors, the less the protection. So a not very simple, complicated firewall with complicated rules is probably worse than having a simple firewall, because the errors will reduce protection effectively. And there are many studies. I have an example there by Wool in 2004, which was later repeated a few years later, and 6 years later, I think. And he showed exactly the same thing, that basically it is the configuration errors, and there are many of them in firewalls, that create the security problems with them. And the other one is the one just below Wool is Groll and others, Groll, Holle, Ruhl and Hollinger and Svers from 2009, who published first the example of having firewalls in an in-vehicle network. In terms of firewalls, we can always expect that there will be errors, and we can always expect that things will go through them. First of all, because they are based on rules. So if they know what the problem might look like, yes, they might catch it. But if they don't know how it might look like, then the threat will go through, the intrusion will occur. So in this case, we need more than firewalls, we need more than preventing intrusion, but we need to detect intrusion. So detecting intrusions can be, and I'll follow here Mitchell and Chen's fantastic survey of intrusion detection techniques, which they have done for cyber-physical systems in 2014, and based on which they can be knowledge-based, they can be behavior-based, or they can be behavior specification-based. So let's start with knowledge-based. A knowledge-based IDS, this is often referred to as a signature-based IDS, intrusion detection system. That's what IDS stands for. And a knowledge-based is one where we know what an attack might look like. So we are aware of different attack patterns. They have been recorded before by having attacked other systems, and or by having been captured by honeypots. Honeypots are fake systems that act as decoys, and their point is to attract attacks. They do this so that we learn about attacks, and also because in this way they do not attack, the attackers will not target the real systems. They will attack these decoys, these honeypots. So we get this knowledge about different types of attacks, and we have an attack dictionary. So effectively it's a list or a database of different attacks and how they look like in terms of the patterns, how they affect the system, what kind of network traffic they might involve, how they affect the memory, how they affect what kind of files perhaps they create. So by knowing how they look like, this is a knowledge-based detection. It means that if we monitor these systems and we see that we see these patterns, well, we know that by going through the dictionary, we see that this is this type of attack, so we know we have detected it because we can see the pattern that we expected. These types of intrusion detection systems are very suitable for conventional computer networks. For example, for anything that is connected to the internet and looks like a normal computer or normal computer network, this is an excellent approach. Because for the vast majority of networks, the attacks that occur are pretty much the same everywhere. So there will be one type of attack that might be experienced in one network. Well, it will also be experienced in other networks. That's almost certain, especially for something that is connected to the internet. So it makes sense to learn from different attacks, create these attack dictionaries, and based on these decide whether our system has been attacked. But of course that means that if something hasn't been seen before, well, an intrusion detection system that is based on knowledge obviously doesn't know it. So knowledge doesn't do us any good there. So in these cases, it might be better to be using a different type of system, which would be a behavior-based system. Now, behavior-based system is often called an anomaly-based system. I don't use the term signature and anomaly because I don't think they are very accurate for cyber-physical systems. So I'll use knowledge and behavior-based as Mitchell and Chen do. So a behavior-based system, a behavior-based intrusion detection system, is one that doesn't know how the attack looks like. So what it does is that it knows how normal looks like. So it knows that, for example, this industrial control system is expected to do that. It's expected to do this. It is expected to measure things in this way, and it's expected to receive network traffic in that way. So there is an expectation as to what is normal. So the car, for example, or the smart lights, all of these are expected to behave in a way. This is their normal behavior, and this is what is recorded. This is what the system knows. The intrusion detection system in this way doesn't know what an attack looks like. It knows what normal looks like. So if an attack occurs and that forces the system to behave abnormally, then this is how we detect that there is an attack. So it is unlike knowledge-based, where we know how the attack looks like. In behavior-based, we know how normal looks like. So the two, they're almost the opposite, the two types of intrusion detection system. Now, why is this important for cyber-physical attacks, for cyber-physical systems? It is very important because cyber-physical systems are not as widespread as conventional computer systems. And more importantly, attacks against them are not as common as against conventional computer systems. That means that an attack that occurs against a cyber-physical system is very likely to be what we call a zero-day attack. So the first time that it is used, the first time that it is recorded. If it is such a thing, if it is a zero-day attack, then knowledge doesn't do us any good because we haven't seen it before. It's 0 day. It's the first day that it appears. And behavior-based instead might be helpful because it will be looking at how the behavior of the cyber-physical system, the behavior of the IoT system perhaps, has started being modified. So if it starts doing things that it is not expected to do, then this is an indication that something isn't going well. So it is an indication that there might be some kind of attack. So this is why behavior-based tends to be, not necessarily in all cases, but tends to be more attractive than knowledge-based when it comes to cyber-physical systems. And there is a second reason why zero-day attacks are an important consideration for a cyber-physical system, and this is that they tend to be critical systems, or they can be safety-critical systems. So if it is a safety-critical system, if it is a car, for example, it is likely that there will be a zero-day threat against it because it will have significant impact, and that makes it attractive for an attacker. If it is an attack against a nuclear facility, for example, this is a high-value target. It is expected that there might be zero-day threats, there might be zero-day vulnerabilities that are exploited, for example, in order to achieve a target. So in this kind of space, it is a wise decision to look first at behavior-based intrusion detection systems that know how normal looks like, rather than at knowledge-based systems that expect that they know how an attack should look like. And then there is behavior specification-based, which is a branch of behavior-based. So this has been shown by Mitchell and Chen. Some of their papers use behavior specification-based systems. It is behavior again, in the sense that it tries to look at what is normal, but it does it based on specification. So an expert, based on the specification, the specs, the specification of a system, specifies, I've said too many times the word specify. So specifies the expected behavior, so the correct, legitimate behavior. If this, let's say, autonomous vehicle, this autonomous train perhaps, goes at a specific speed, then this is the speed that should be expected. If the speed is below that or above that, then there is an indication that something might be wrong. And if one looks at many different of these aspects of a system's behavior, or let's say of a cyber-physical system's behavior, then one can build a picture as to whether it is performing in the way it is expected by its specification. I mentioned that the intrusion detection system, what it does is that it monitors the state of the system, let's say the state of the vehicle, and tries to see if there is any indication of an attack. Now, whether it is knowledge-based or behavior-based doesn't matter in this case. What it does is data-driven either way. So it tries to collect data regarding the state of the vehicle. So it might be collecting things like the network traffic characteristics, like the packet sources, the different packet destinations, the timestamps, traffic rates, the types of messages that are received, generally any kind of information related to the cyber aspects of this vehicle in this case. But in cyber-physical detection, for cyber-physical attacks, one can also use physical input features, so physical data to be monitored. Let's consider the case of a SCADA system. So if the rate of change of the water level is limited by the capacity of the tank, of course, which it is, and the diameters of the pipes, again, which it is, well, then perhaps we can use this for the IDS. Because this is a physical, it's a physical law in a sense. You cannot have a water storage tank go above its capacity in terms of the rate of change of the water level. It is determined by its physical properties, for example, by the diameter of the pipes. So if we see that there is a lot more than that, in general that the level of water is at a level that is not correct, that can't be physically possible, then this is an indication of an attack. So this can be used as part of the intrusion detection. So this is something that you cannot do in normal conventional computer systems. You cannot be measuring, for example, the weight of the mouse or the color of the monitor. That won't make a difference. But you can measure such things in cyber-physical systems. So in this case, you can measure the rate of change of the water level in the water storage tank. And another one is that you can start measuring things related to the physical characteristics of the actual technology implementation. So if one uses GPS for the navigation, for finding its location, then a spoofed, so a fake GPS signal, one that comes from a terrestrial source rather than the real GPS satellites, will be a lot stronger than a legitimate one. Why is that? Well, because it comes from much closer. It comes from somewhere on the Earth, while a GPS satellite signal will come from a satellite. So you can have an indication about whether the GPS signal that, let's say, a driverless car receives is legitimate based on the signal strength. And in fact, you can use the signal strength for other things too. For example, if let's consider the case of an implantable medical device, and there is an implant, and so let's draw this actually. So this is the body, there is an implant inside the body, and there is some kind of control device on the body, and they communicate via wireless. Okay, so this is inside the body, so this is inside, and the other one is outside. So what happens is that the communication will have to go through the body, through the skin there. So the variation of the signal strength between the two devices, so the implant and the on-body control device, will be much lower than if you had a fake one. So let's go again. So and they have the implant. There's the implant. And there's the legitimate one. And then there is a fake one. So this is a fake. Let's say this is an attack device. Now, if this device communicates with the implant, well, the variation in the signal strength will be greater. It has been shown by Shi, Li, Yu, and Yuan in 2013 that this is a usable mechanism for detecting if there is an attacker in the case of implantable medical devices. So what we did is that we actually measured the characteristics of the physical characteristics of the technology implementation. So in this case, the physical characteristics of the wireless communication between something that is inside the body and something that is far from the body, rather than something that is attached to the body. Okay, so the signal strength is much greater. The variation of, not the signal strength. Sorry, let's see it again. The variation of the signal strength will be much lower in the first case than in the second case. And you can extend all these ideas by having many more cyber and physical sources of data for monitoring a system's health. Now, this is an example from a paper of ours in this case, which shows how to offload the processing of the IDS, of the intrusion detection task, to a cloud service, and from there detect effectively an IDS as a service, example. But it doesn't matter. Let's focus on this part, which is the different aspects that are monitored on this robotic vehicle in order to detect if there is any kind of attack. So this is the attacker on this side. The attacker is sending rogue commands to this robotic vehicle, so as to hijack it perhaps, or to cause it to crash. And the robotic vehicle on its own is collecting data, which it sends later to a process for monitoring, for analyzing. So this data can be related to the compass. So is the compass measurement meaningful, or does it keep changing all the time for no reason? How about the energy consumption? How about the vibration of the chassis? We have actually seen that in some types of attacks, for example, when they cause loss of network connection, like in denial of service attack or in jamming attacks, then there might be vibrations or minute vibrations caused to the chassis of the vehicle, caused by the fail-safe systems on the vehicle that force it to stop and restart every time it loses connection. So this would be one example of a physical impact of their attack, in this case at least. They have some sensors for detecting obstacles, and they're measuring the speed also of the actual speed of the vehicle for the different wheels. So all of these are measured on the vehicle, and the vehicle is either on its own or by sending it to a more powerful infrastructure, like in this case this cloud infrastructure. It determines whether it is under attack or not. This can be knowledge-based, so it might have been subjected to different types of attacks before, and if it sees them again, then it determines that it is under attack. Or it might be behavior-based, in which case it knows how it normally behaves, and if it feels it doesn't behave normally, then this is an indication that it is under attack. And a few more examples of data sources that can be used in the case of cyber-physical systems. So one for, let's see, for GPS spoofing, GPS signal, we'll have here GPS signal strength for GPS spoofing. For any kind of command injection attack, for example, for these vehicles, it might be the speed variations, how the speed of the vehicle changes for each wheel, or the rate of change of the water level that we mentioned, a variation in the received signal strength, as was the case for the implantable medical devices. It can be the duration of the message exchange, if it happens very quickly or very slowly. It can be the power consumption. That's very important, because some attacks actually target power consumption, especially when it comes to medical devices. Also for military sensors, for industrial control sensors, because if their battery is depleted, then they're useless. So it might be a target of an attack, the power consumption. Similarly, the voltage, the current phase, and the actual location, in fact. So where is it? Was it meant to be here? Could it be here at this point in time? Or is it now accessed by something that has a location that is very different to the actual device? So how is this possible? So all of these are physical input features. These are unlike unlike conventional cyber intrusion detection, which looks at only network traffic, memory, files. All of these cyberspace characteristics. For cyber-physical systems, one can also look at physical input features. So this is a very important change, a very important new aspect in intrusion detection. And based on this, let's do an example, or actually an exercise. So this is effectively homework in this case, and so let's see this homework. Consider this driverless pod car. So this is like a little pod car that you might see in some of the very modern airports. And what it does is that it can carry one or two, or perhaps more passengers in over short distances. In this case, we have a very specific route, which is completely straight to make things easier from the perspective of the exercise. It starts at here on the left side, which is 0.0 meters, and it goes here, which is 2 kilometers. Okay, so this is the source. This is the beginning, and this is the end of this route. This is where it starts. This is where it finishes. And the pod car has a roof-mounted GPS. And what it does is that the GPS tells it where it is. So we find out about X position. So where are we in this space, based on a GPS, which, being the GPS, of course, cannot be completely accurate. So I have chosen here that it might be off by, let's say, up to 3 meters, plus minus 3 meters. So it can be 3 meters either side of X, of where it thinks it is. And there are also some front-mounted sensors for detecting obstacles. And also, it is normally fully autonomous. But it can be semi-autonomous, or it can be the case that an authorized operator can wirelessly send commands if there is an emergency. So there is a human operator, there is someone seeing it somewhere at the control center. They see the vehicle, and if they see that something might be wrong, that someone is on the lines or something, then so an authorized operator, someone who has an ID that is authorized, can wirelessly send commands and operate it remotely. Now, the speed of the pod car physically can be up to 20 meters per second, so it has the ability to go up to 20 meters per second, but it is limited, it is technically limited to 10 meters per second when it is in autonomous operation. That's because for comfort and also safety, they shouldn't go faster. Its collision avoidance sensors would not perhaps be able to detect the obstacles quickly enough in any other case. So if it was going faster, it wouldn't be seeing the obstacles quickly enough to stop. Okay, so this is the setting of the exercise. There is a pod car. It estimates its position its position X based on GPS. There is a plus minus 3 meters there error. There are sensors for detecting obstacles. The speed can be 20 meters per second, but it is limited to 10 if it is autonomous. If it is not autonomous, it is not limited, and this is for comfort and safety. And there is a communication protocol now. So this is where the cyber part comes in. The communication protocol is as follows. It's very simple. The operator, so the operator is someone who would be here, for example, can send start, stop, or travel at, let's say, 12 miles per hour speed instructions to the pod car. And it does so in single 80-bit packets containing also the operator's ID and the pod car ID. If there are many pod cars, there will be the pod car ID there. If there are many operators, that will be the operator ID there. This is a single 80-bit packet, and it has 3 possible commands: start, stop, or travel at, let's say, 10-12 miles per hour, so which is specified there with the X there. Note that this X is different to this X, so this is, I shouldn't call it X, let's call it Y, at Y speed rather than X, so it's not to confuse it with the X location. The pod car then sends 40-bit ping packets to the operator every 5 seconds. What it does is that it tries to see if it is alive, if the connection is alive. If the connection is there, if there is still a connection, wireless connection between the pod car and the operator, this is checked by ping packets that are sent every 5 seconds, and they are initiated by the pod car. So it's the pod car that is sending them. It is effectively a heartbeat packet. It tells the operator that it is there, it is there, it is there. It does that every 5 seconds. And for every packet, whether it is an instruction or whether it is a ping, there is a 40-bit acknowledgement packet. So whichever of the two, whether it is the pod car or whether it is the operator that receives a packet from the other side, then they have to send back an acknowledgement which is 40 bits. The wireless link can support only 1 kilobit per second in either direction. Obviously this is a ridiculously low value, but I'm doing it to simplify the maths in a way. And the pod car stops immediately if it receives no acknowledgement. Or it stops immediately if it has reached its destination, of course, and also it stops immediately if it has detected an obstacle within 10 meters. So these are the different characteristics of first the actual vehicle, the actual pod car, and then its communication protocol, so how it communicates with the operator. And there is the exact exercise now. These are the questions. So question 1, so this is the homework part. So question 1, what rules would you consider including in a behavior specification intrusion detection mechanism running as part of the embedded software of this pod car? So this is a mechanism that is running on the pod car's embedded software. It is based on rules. It is based on rules for energy efficiency, also for being efficient in terms of processing, because it is an embedded system and the processing power is very limited. Okay, so this, and also it is a behavior specification intrusion detection system, which I remind you, behavior specification means that it depends on the specification, and the specification is what we saw before, this and this. So the specification is for example, the plus minus 3 meters of the GPS, the 80-bit size of the packets, and so on. So these are the specifications. So based on the specifications, create a rule-based intrusion detection mechanism as part of the embedded software of this pod car. Effectively create the rules. As processing power is limited, the detection mechanism cannot check all rules continuously, but only once every 10 seconds. So it can check all rules every 10 seconds only. The only data available are the following: the total number of packets sent PS. I'm not giving you numbers, so I'm only telling you that they are called PS, so just use PS as it is. The total number of bits sent BS, the total number of packets received PR, the total number of bits received BR, and the GPS location X. Now again, I remind you there is a plus minus 3 there. The difference between the current value and the value 10 seconds ago for each one of these is denoted with the Greek letter delta. For example, delta PR will be the total number of packets received in the last 10 seconds, and delta X will be the total distance that is covered in the last 10 seconds, according to the GPS module. So delta X is in a sense an indication of speed. Okay, so this is question 1. What are the rules that you would consider including in this or in a behavior specification IDS system? And question 2, which of the rules that you've defined in question 1 would be violated during 1. A denial of service attack based on a flood of illegitimate instruction packets of 80 bits each? Okay, so 1 in question 2, there is a denial of service attack which floods the system, the network, with illegitimate instruction packets of 80 bits each. Second, there is a jamming attack on the wireless channel, so there can be no communication on the wireless channel. Third, a GPS spoofing attack, so the location that the vehicle of the pod car determines is not the correct one because it is affected by a spoofed GPS signal. The fourth one, a command injection attack that aims to increase the speed of the pod car up to an unsafe 20 meters per second. So the attacker has injected a command to increase the speed beyond the 10 meters per second without the authorization of the authorized operator, of course. And the last one, a malware attack against the control center. Actually, no, the last one is this one, or a code injection attack. So in question 1, you define the rules based on the specification. In question 2, you see which attacks could be caught with these different rules that you have determined. So let's see how you can do.